shared with our seminar. It's my pleasure to introduce the speaker of our seminar for today, Professor Amnon Neeman, and he will speak about vanishing negative K-theory and bonded T structures. Please.
Thank you very much. Thank you for coming to the talk. So, to begin, let me remind you of an exact category. So an exact category is an additive category where you know what the short exact sequences are. So I remind you, if the category is abelian, then a sequence E dash goes to E goes to F, E double dash is short exact if F is the kernel of G and G is the co-kernel of F. Now, to be an abelian category is a property, not a structure. So if I give you a category, either it's abelian or it's not. So to be abelian is the statement that finite limits and finite co-limits exist, that the natural map from the co-product to the product is an isomorphism, and some other properties. Anyway, it's a property. And the short exact sequences are given by kernels and co-kernels. In other words, a sequence is either short exact or it's not. But in an exact category, somebody tells you what the short exact sequences are. So that's a structure, and they must satisfy some axioms which I won't repeat. Now, examples of abelian category, of exact categories, are all abelian categories with the usual short exact sequences. And the next major example is a full subcategory of an abelian category closed under extensions. And the most important example in this talk will be the category of vector bundles on an X. Now, just to remind you, to give an exact structure is a structure. I tell you what the exact sequences are. And in particular, given any additive category, there's always the stupid way to turn it into an exact category. You declare that the split sequences are exact. So an additive category can well have more than one exact structure. For example, if the category is abelian, it has the stupid structure, the structure where the split exact sequences are the exact ones, as well as the natural structure that comes from its being abelian. And if you take the category of vector bundles, so let's take the category of algebraic vector bundles on a scheme, then it has the usual exact structure that comes by viewing a short exact sequence of vector bundles as a sequence that's exact as a sequence of abelian groups. And this agrees with the split exact structure if and only if X is affine. Okay, the next major definition I want to remember is that of the Grothendieck group. So if you're given any essentially small exact category, you define the Grothendieck group to be the free abelian group on the objects divided by the relation that every time you have a short exact sequence, the middle term is equal to the sum of the outside terms. And because the category of vector bundles plays such a big role in this talk, we will abbreviate K0 of X will stand for K0 of the exact category of vector bundles on X. The next thing I'd like to remind you of is the Meyer-Viatori sequence. So if you're given a scheme and two open subsets U and V, then just by functoriality, you have that the vector bundles on any on any set restrict to vector bundles on any open subset. And this is an exact functor of exact categories. So you get a commutative square of exact functors, exact restriction functors. And if you take K0, it induces a commutative square of abelian groups, which you can fold into a sequence composing to 0. And an old result is that if X is the union of U and V, in other words, if U and V cover, then this sequence is exact in the middle. It's the only place, okay, it's the place it's exact. And now, one way to think of higher K theory is that you'd like to turn it into a long exact sequence. So this can be done. There's a way to define both positive and negative K theory in such a way that this sequence becomes long and exact. And of course, this has other properties which we will not mention. In this talk, the major fact we will use is the long exact sequence in algebraic K theory, positive and negative. And now comes the observation that if you take the special case of the category of vector bundles on a scheme, so this is the category of algebraic vector bundles on a scheme, then there are old and classical vanishing theorems on negative algebraic K theory. So let me recall two of them. So, this follows from all the results of Bass, but in this generality, it was conjectured by Weibel in 1980 that if X is an Euclidean scheme of dimension n, then the negative K theory vanishes. So Kr of X vanishes for all r less than minus n. And that conjecture, well, okay, I'm rushing to the end. Special cases were proved over the decades. There was gradual progress, but the final positive result, so the complete proof of the conjecture, was by Kertz, Strunk, and Tame in 2018. So Weibel's conjecture is now a theorem. What we would like to discuss is a conjecture due to Schlichting. So let's begin with his theorem, which again is an improvement on earlier results in the affine case. So it is a theorem that if X is Noetherian and regular, so not just Noetherian, and finite dimensional, then all of the negative K theory vanishes, not just the very negative, not just below dimension minus n. And so Schlichting proved this, but he also conjectured the major generalization. And to state his conjecture is general. It's not just about schemes. So for any E, there's a recipe to produce a K theory out of it. And we have focused on the case of E being the category of vector bundles. But the relevant thing here is that if X is regular and finite dimensional, then there's an abelian category with the K theory of the vector bundles being equal to the K theory of A, and you can take A to be the category of coherent sheaves on X. And Schlichting's conjecture says that for any abelian category, all of its negative K theory vanishes. So the reference is to Marco Schlichting's thesis. It appeared in 2006. And for us in this talk, it will be conjecture A. Okay, so this is conjecture A. And conjecture A comes with a plausibility argument. So let me go through the plausibility argument. But okay, first let's say what Schlichting proved. He proved that if the abelian category A is Noetherian, then all of the negative K theory vanishes. And for any abelian category, he proved the vanishing of K minus 1. Okay, now for the plausibility argument. So there's an old theorem of Quillen which says that if you take an abelian category B, inside it a Sayre subcategory A, and then you form the quotient C, which is B mod A, then there's a long exact sequence in K theory which stops at K0. So the map from K0B to K0A is surjective. So if you look at this long exact sequence and you say, well, as long as I don't leave the world of abelian categories, I don't see any negative K theory. The long exact sequence terminates at K0. So the question becomes, can you define negative K theory for abelian categories without ever leaving the world of abelian categories? And philosophically, the way you should do it is use the general long exact sequence in K theory and do dimension shifting. So in order to do dimension shifting, you would try to embed A into an abelian category B with vanishing K theory, because then all of the diagonal maps would be zero. Would be isomorphism. So you see, if the K theory of B vanishes, if the middle column is all zero, then all of the diagonal maps are isomorphisms, and the vanishing of K minus 1 of C would force the vanishing of K minus 2 of A. So you would have a descent argument, a dimension shifting argument. So what do you want? We want to embed any A into an abelian category B with vanishing K theory. And the natural thing to do is to try to use the Eilenberg swindle. So to make B a category that has countable coproducts. And why would this force the K theory of B to vanish? It's because of the Eilenberg swindle. You can form the functor F from B to B, which takes an object B to the countable direct sum of B with itself. And then you have the isomorphism that F of B is canonically isomorphic to B plus F of B. And if you apply K theory, you get that Kn of F is Kn of the identity plus Kn of F. And by the magic of subtraction, you get that Kn must take the identity to zero. So the K theory has to vanish for formal reasons. But the problem with this approach is that if you take A and embed it, well, first of all, you can always embed A into an abelian category which contains countable coproducts. You just take A and embed it by Yoneda into a module category. And the module category has all coproducts, so you can look at the smallest subcategory of that containing A and closed under countable coproducts and call that B. So you can certainly close A under countable coproducts, but the cat A is almost never going to be a Sayre subcategory. And the reason is that if you take any countable collection of morphisms with the same codomain, so morphisms Fi from Ai to A, then in the category B, which is countable coproducts, you can form the map from the coproduct into A. Now, in the category B, which is an abelian category, this map will have an image, and the image will be a B subobject of A. Now, if this is a Ser subcategory, if the category A is Ser, then this B subobject of A must lie in A. But the image of this map will almost never be in A. It's somehow an assertion that there is a maximal image among the countable ones. So you can also begin to see why the Noetherian hypothesis might help. So, anyway, so although the argument seemed plausible, nobody could make it work. And that's how things stood for about 15 years. And the next major progress came with this 2019 paper by Antje, Gepner, and Heller. So this is a lovely paper, and I'm going to be talking about it for most of the rest of the talk. So first of all, this paper generalizes Schlichting's result. So it says, if you take a model category with a bounded T structure, then as long as the heart of the T structure is Noetherian, then all of the negative K theory of T vanishes. And unconditionally, it says that K minus 1 of T is 0. So first of all, I should note that this is a generalization of Schlichting's results. So if A is an abelian category, Schlichting's result come about by putting T, the bounded derived category of A, with a standard T structure. But not only is it an improvement on Schlichting's result, it's somehow, it's a wonderful result in many ways. I mean, one of the ways it's a wonderful result is that it tells us that there are obstructions to the existence of bounded T structures. I mean, think about it. We've always thought that there are lots of T structures and lots of bounded ones. We know many ways of producing bounded T structures. If you, the original paper by Behlens and Bernstein and Deligne, which introduced bounded T structures, told us that any recollement will allow you to glue two T structures on the outside pieces to a T structure on the middle. And bounded T structures glued to a bounded T structure. So that's one way. There's the 10 years later, the paper by Happel, Reiten, and Smaleur, which told us how to tilt a bounded T structure with respect to a torsion pair. This has proved very useful. Approximately 10 years later, there's the paper by Alonso, Jeremias, and Saurins, since much generalized by many authors, which told you how to take a set of objects and use them to generate a T structure. And there's later literature on when this T structure gives interesting bounded T structures on subcategories. And finally, there's the method of Bridgelands, where you construct T structures, in fact, stability conditions, by filtering objects using the most destabilizing sub-objects with respect to a central charge. So this gives us at least 4 ways to cook up lots of bounded T structures. And somehow all of the intuition is that it's easy to construct bounded T structures. And here's a theorem that says that it's obstructed. It goes against the intuition. Okay, so Beyond that, there's the K-theory aspect. It greatly generalizes the Schlichting's result, but it also greatly generalizes Schlichting's conjecture. So Antio, Gepner, and Heller went on to say, well, if Schlichting's conjectures this, why don't we conjecture much more? And okay, here's the conjecture. Let T be a category, any model category with a bounded T structure, then all of the negative K theory of T will vanish, not just K minus 1. So this is conjecture B, where the numbering is according to their paper. And then there's a conjecture C. So conjecture C, if conjecture B is true, then conjecture C is a consequence. That conjecture B is the strongest conjecture. It implies both conjecture A and the conjecture I have there. So yet another conjecture says that in any case, the map from the K theory of the heart to the K theory of T should be an isomorphism for all n. Okay, it's known for positive n. The conjecture is that it's an isomorphism also for negative n. And again, according to the numbering of the paper by Antio, Gepner, and Heller, this is conjecture C. And this conjecture also came with a plausibility argument. So the plausibility argument runs like this. If you take a category S, and inside, so a DG category if you wish, and inside it a DG subcategory R, and form the DG quotient in the sense of either Keller or Drinfeld, then there's a long exact sequence in K theory. And if you could do it, if you're given R with a bounded T structure, and you could produce an S with vanishing K theory, and such that T also has a bounded T structure, then just as before, because the middle column is zero, all the Ki of S would vanish, all of the diagonal terms would be isomorphism. So the vanishing of K minus 1 of T would imply the vanishing of K minus 2 of R, and you could use dimension shifting to prove the conjecture. And you see, if you believe the philosophy that bounded T structures are easy to produce, how difficult could it be to do this? After all, you're starting with a category R with a bounded T structure, and you're asking for a category S with vanishing K theory, such that the quotient S mod R has a bounded T structure. Surely all this take is some cleverness with bounded T structures. How difficult could it possibly be? So let me tell you how I came across this conjecture. So the first I heard of this beautiful paper by Antio, Gepner, and Heller was when I happened to be in Boston and I heard a talk by Gepner about it. And so this was in 2018. And then later in 2018, Gepner moved to Australia and he gave more talks about this result. So I went to at least 2 talks, one in Sydney and one in Canberra. And every time I heard this talk, I would tell anyone who wanted to listen that it's an amazing paper. It's many beautiful results. But in particular, this plausibility argument should be turned into a proof. How difficult could it possibly be? And then came 2020, and as you might remember, with it came COVID, and we all got locked down. And there's not a whole lot to do when you're locked down in Canberra. So I decided, why not? Let me try to prove it myself. How difficult could it possibly be? All it required is some cleverness with T-structures, bounded T-structures. Well, so the upshot is that this isn't difficult, it's impossible. So conjecture A and conjecture B are both false, and the counterexamples appeared in this paper. And now I'd like to tell you about the counterexample because I want to indicate what parts of it could be improved. So I want a counterexample. So I need to produce for you a category with a T-structure, a bounded T-structure, and such that the negative K theory is non-zero. So I want a triangulated category with a bounded T-structure. Let me actually introduce 3 triangulated categories. So one of them will have a bounded T-structure, and the other 2 will be useful in computing the negative K theory. So let's begin with an idempotent complete exact category. So E is any idempotent complete exact category, and KB of E will be the usual homotopy category. So the objects are bounded cochain complexes, and the morphisms are the homotopy equivalence classes of cochain maps. Just our old friend, the homotopy category. Now, inside it, we want to consider the category of acyclics. Now, normally, when you say that a cochain complex is acyclic, this means that the image of one map is the kernel of the next. But in an exact category, you don't know what the image or the kernel, I mean, you're not given the existence of images and kernels. So the correct definition of acyclics turns out to be that all of the morphisms in fact have images. So in other words, you postulate that each delta I factors to a ki in such a way that the sequences ki goes to ei goes to ki plus 1 are admissible short exact sequences. So in other words, the long sequence is pieced together from a whole lot of admissible short exact sequences. So it's an old theorem of Thomason's that if E is idempotent complete, this actually is a triangulated subcategory, in fact, even a thick subcategory of KB of A, and you can form the quotient, which is usually called the bounded derived category of E. So these are our 3 subcategories. So as I said, one of them will have a bounded T structure and the other 2 will be useful for computing K theory. So now for the bounded T structure. So the category with bounded T structure is the category of the acyclics. So in order to give you the bounded T structure, I have to tell you which are the negative objects and which are the positive objects. So here's the definition. The negative objects are the ones which vanish in all positive degrees, and the positive objects are the ones that vanish in all degrees less than -2. So I assert that this is a bounded T structure. Okay, because this is somewhat strange, let me go through the proof. So the bounded part is easy. So to say that a T structure is bounded is to say that if you take any object in the category and shift it far enough to the left, it will be negative. And if you shift it far enough to the right, it will be positive. And that's obvious because of the boundedness. Because every object vanishes outside a finite range. The next thing you need to know is that the negative objects are closed under shifts to the left, which is visibly true, and that the positive objects are closed under shifts to the right, which again is obviously true. So the first thing that needs proof is that there are no non-zero morphisms from the negative objects, from the less than or equal to 0 to the greater than or equal to 1. So remember, a morphism would be a homotopy equivalence class of a cochain map. So choose a representative, choose a cochain map. I need to show that it's 0, meaning I need to show it's null homotopic. So let me go through the proof. So if you look at the red square, it must be commutative, which means that the two composites from E0 to F1 vanish, which means that but in fact, the bottom row is exact, which makes delta minus 1 the kernel of delta 0. So the map G must factor uniquely through delta minus 1. So there exists a unique theta making the red triangle commute. So I recall on the right, then I have that the two composites from E minus 1 to F0 must be equal. But, so these are the two composites in red in the diagram. But these two paths from E minus 1 to F0 are also equal, just because this is a cochain map. And therefore, all three paths from E minus 1 to F0 are equal. And in particular, the two red paths, let's forget the path that goes through G, the two red paths are equal. But the map delta minus 1 is the kernel of delta 0, so it's a monomorphism. So therefore, the triangle commutes. So now we've proved that both triangles commute. So theta must be a homotopy of the cochain map with 0. So therefore, it is indeed true that there are no non-zero maps from E star to F star. And finally, in order to complete the proof that this is a T structure, I need to take any object and exhibit it as an extension of a negative by a positive object. And the way I do it is I recall that this is being acyclic means that each morphism comes with an image. So I let K0 be the image of E minus 1 to E0. And this allows me to form these cochain maps below. So if you stare at this, everything inside commutes. It's a series of cochain maps. And it exhibits the second row as an extension. So in fact, this is a distinguished triangle in the homotopy category. One way to say it is that the mapping cone on the map between the bottom two rows is the second row, and it exhibits the second row as an extension of an object by in the less than or equal to 0 by an object in the greater than or equal to 1 part. Okay, so this completes the proof that this is a bounded T-structure. Now we have to try to compute the negative K-theory. So, okay, before we compute the negative K-theory, I should remind you of the heart. So the heart of this T-structure has for objects the short exact sequences. So the sequences E minus 2 goes to E minus 1 goes to E0. And the morphisms are the homotopy equivalence classes of cochain maps. And the general theory tells you that this category is abelian. And remember, being abelian is a property. If I give you a category, then either it's abelian or it's not. And I don't have to tell you what the short exact sequences are. You know. Anyway, so this category is abelian. Okay, now for K-theory computations. We want to be able to compute the K-theory, and for us, and now we go back to the 3 categories we started with. So we have that the bounded derived category of E is the quotient of the homotopy category by the acyclics. And this, okay, once you choose appropriate models, this gives a long exact sequence in K-theory. And I'd like to use this long exact sequence to compute the negative K-theory of the left column. And the point is that the other 2 columns I know. So the middle column is the K-theory of E with the split exact structure. And the right column is the K-theory of E with the natural exact structure. So in order to find a counterexample to the, if the conjecture is true, then the left column is going to vanish. And so the horizontal map on the right would have to be an isomorphism. So all I have to do is exhibit an example where the horizontal map is not an isomorphism. So this would kill conjecture B. Now, once we're in the business of killing conjectures, why not try to kill 2 conjectures with 1 stone? So if you want to kill both conjecture A and conjecture B, then we'd be interested in situations in which the natural map from the K-theory of the heart to the K-theory of E, of the acyclics, is an isomorphism. So for this, it helps to know, to prove the theorem, that the natural map from the bounded derived category of the heart, the realization factor of Valence and Bernstein and Deligne, is an equivalence of triangulated categories if and only if the category E is hereditary in the usual sense of representation theory. So xi of E dashed vanishes for all I greater than 1. So this is a necessary and sufficient condition. And it tells us that as long as E is hereditary, the map from the K-theory of the heart to the K-theory of the acyclics is an isomorphism for all N. And a special case of interest is if Y is any algebraic curve, then the category of vector bundles on Y is hereditary because of the spectral sequence. There's a spectral sequence whose E2 term is HI of the local xj, And for vector bundles, we know that the xj vanishes for j greater than 0. And for curves, we know the vanishing of hi for I bigger than 0, 1. And the corollary informs us that for any algebraic curve, you would have that the map from the K-theory of the acyclics, of the heart to the K-theory of the acyclics, is an isomorphism for all n. So, in the published paper, I specialized to singular projective curves with singularity, with simple singularity is no worse than single nodes. With some amount of work, I proved that k minus 1 of E plus is 0, and there are known examples where k minus 1 of E isn't 0. And that gives the counterexample. And if you look at this diagram, you remind yourself how the argument goes. So with some amount of effort, I proved that the term in the top row in the center is 0, and therefore the first diagonal map, so the map from k minus 1 of E to k minus 2 of the acyclics, is injective, but k minus 1 of E is non-zero, so therefore k minus 2 of the acyclics is non-zero, and this kills both conjectures. So this is how the argument in the paper goes, but much to my regret, I have to tell you that there's a much better argument. So the part in orange, I can do much better. So I don't know why this happens. After the paper is published and you can no longer change it, you discover that there's a much simpler, better, and more elegant proof. So this is a general statement. You will always find a better proof eventually. And now, let me try to explain my stupidity away. So, my excuse, for what it's worth, is that I wasn't sure I believed the statement in orange. I found the statement in orange surprising. I mean, I could try to explain why it surprised me, but let's not dwell on my stupidity too long. So because it surprised me, I was very careful about the proof. I checked it, and I committed the crime of getting bogged down in the details of the proof to make sure that this surprising result really was true. And I failed to ask myself the important question, which is, why is this surprising result true? So the correct argument, the much better argument, would have been to say that the right theorem is that if you take any idempotent complete additive, category in which all the endomorphism rings are Artinian, then all of the negative K theory of E plus vanishes. So not only is this true, it's true, and once you see the proof, it's easy. So why is this? There's an old theorem, essentially due to Bass, that if you take any Artinian ring, then its endomorphism ring has vanishing negative K theory. And now, if you take any object in an idempotent complete exact category, then the endomorphism ring, the K theory of the endomorphism ring of this object is also the K theory of the full additive subcategory of all objects generated by E. So in other words, it's all direct summands or finite direct sums of E with itself. And as you take the object E bigger and bigger, in other words, as you can always form finite direct sums of objects in the additive category. As you take bigger and bigger objects, you get that the entire category becomes the filtered colimits of these additive categories generated by objects. So for each of these additive categories, subcategories, you have vanishing negative K theory, and in the direct limit, this shows that the negative K theory of E is 0. Okay, so now that you have the theorem, let's go back. It tells you that as long as E is chosen to have Artinian endomorphism rings, the entire middle column will vanish. So all of the negative K theory of E plus will vanish. So all of the slanted arrows will be isomorphisms. So this gives you many examples in which you can compute K minus I of the acyclics, and many examples in which it's non-zero. And so somehow it's a much more general phenomenon than my old proof showed. And there are many examples in which the category isn't hereditary, and therefore the natural map from the derived category of the heart, so the realization functor is not an equivalence of categories, so it isn't obvious that the negative K theory of the heart is the same as the negative K theory of the acyclics. And if nothing else, this means one could now check, one could now test whether conjecture C is also true. So I said that this talk will have many open problems. Here's one. Try to understand whether conjecture C, or try to test conjecture C on the many new counterexamples. Okay, let me go back to this wonderful theorem of Antioch, Ebner, and Heller. So I spent a lot of time about the K theory aspects. So trying to sharpen the K theoretic statement. But there's also the obstruction. I mean, as the title of the paper says, there are K theoretic obstructions to bounded T structures. And in particular, if X is a finite dimensional Noetherian separated scheme with enough vector bundles, and K minus 1 of X, then the K minus 1 of X is non-zero, then it follows from the theorem that the bounded derived category of vector bundles on X has no bounded T structure. And if Kn of X is non-zero for n less than or equal to minus 2, then any bounded T structure on the bounded derived category of vector bundles cannot have an Noetherian heart. So this corollary is in the original paper of Antioch, Ebner, and Heller. And based on this corollary, they formulated a conjecture which says that the category of vector bundles is a bounded T structure if and only if X is regular. So this is conjecture 1.5 in their paper. And I should say that on the basis of the evidence available at the time, this was a daring conjecture because the K-theoretic evidence, there are many singular schemes, so schemes which are not regular, but where the K-theory vanishes. For example, all zero-dimensional schemes. So the evidence given by the corollary is relatively thin. It's quite possible for the K-theory to vanish, but for the X to be singular. So on the basis of the evidence, this conjecture was daring, but the best conjectures are the daring ones that turn out to be true. And so here comes a theorem. And the theorem says that not only is the conjecture true, but the major generalization is too. So let X be a finite dimensional Noetherian scheme with enough vector bundles. And let Z be any closed subset. Let dB sub Z of the vector bundles be the category whose objects are the bounded complexes of vector bundles, which are acyclic when restricted to the open subset X minus Z. Then the theorem says that the bounded derived category of vector, this relative bounded derived category, has a bounded T structure if and only if Z is contained in the regular locus. So, if and only if there's an obvious bounded T structure. And the proof is in this preprint. And what as I said, in this talk, I wanted to stress the open questions. So what this theorem shows is that there must be some other obstructions. I mean, the beautiful article by Antje Gepner and Heller showed that the existence of bounded T structure is obstructed. There are K-theoretic obstructions. But here's a theorem that says that even when the K-theoretic obstructions vanish, you can still have theorems which say that there are no bounded T structures. So, so I should say that the proof of this theorem is not obstruction theoretic. It goes by way of metric techniques. It goes by other methods, methods I really don't want to discuss in this talk. But it means that there must be some other obstructions, not K-theoretic, and somebody should figure them out. Trying to understand obstructions to the existence of bounded T structures is very valuable, given how many conjectures there are about the existence of bounded T structures. Okay, let me stop here. Thank you very much.
So, thank you so much for your very nice talk. Are there any questions, comments? There is a question by Xia Wu on a chat box. Can you see it?
I have to figure out how to go back. Sorry.
I can read the question for you.
Yes.
Do you mean that the conjecture C, the K group is in the positive degree are the same?
Yes, so this is a theorem. The K, So it was proved, there are two proofs in the literature. There's an old proof of mine, and there's an infinity category proof due to Clark-Barwick. Anyway, that is a theorem. So that theorem is from before Schlichting's paper. At least my theorem is from before Schlichting's paper. So it's from a time when people didn't really know how to define negative K theory in this generality. And Barwick's theorem is also only about negative K theory. It's only about positive K theory. But in any case, it's a theorem that the map in K theory is an isomorphism for positive N. And I don't know if you believe. Yeah, okay, I don't know what to believe. But the conjecture of Antiochus and Heller is that the theorem in positive K theory should generalize to negative K theory.
Are there any questions, comments? Oh, it seems there's no question. So let's thank Amnon and all the speaker of today. Thank you very much.
Thank you.